y'all doing? Hey, sorry, that's too loud. Hey, I'd like to introduce you to Mark Clattenberger. He's in the Webb Space Flight Center clean room. He's one of our, he's actually one of our electrical engineers that's working on constructing the Webb Telescope right now. At the Webb Space Flight Center, we have the world's largest clean room, and all or most of the components of the Webb Telescope are showing up there, and that's where the majority of the Webb is going to be constructed. So, hey Mark, how you doing?
Doing great. How are you?
Good. Hey, thanks for joining us again and coming in on a Sunday.
No problem.
So Mark's here. He's going to tour us around a little bit. But if you have any questions you'd like to ask Mark in the middle of the tour, raise your hand, come on over, speak to him. It's a one-on-one thing. So feel free to jump in at any time. So Mark, first off, you're wearing some kind of a funny outfit there. What is that?
Hey, what are you talking about? This is what I always wear. No, this is a clean room suit. Here, I'm going to hand out a little. It's completely encapsulates your body. As part of the process of coming into the clean room, you have to be very careful not to contaminate the instruments, the optics, and that's the biggest issue, the optics themselves. You definitely contaminate them, of course.
So, but you've got your street clothes on under that, right?
Yeah, absolutely.
Hey, so can you kind of show us around the clean room a little bit?
Absolutely. Behind me, that black item there is the structure that holds the cameras for JWST. There's one in there. We'll get a closer look at that in a second. And let's see if we pan around the room. I'm going to start over here with the filter wall. This is where all of the air comes through the room. Behind this giant wall, it's about 100 feet tall, are a series of HEPA filters that really get the smallest of particles out of here. And obviously, again, for contamination reasons. And then if we pan around a little bit here, I'll go around this way this time. Let's see, that thing there, actually, that thing right there is a piece of equipment to rotate the structure so that we can work on it more easily. As you'll see here, this structure is, a lot of the electrical connections are up at the very top, so we can put it on that structure and rotate it down so that we can get to the connectors without having to work over the instruments. And while we're here, that gold cylinder looking item there is called a Miri core. It's for one of the instruments. It's to bring it down to about 15 Kelvin. Believe it or not, even in deep space, it's not quite as cold as they would like it for the detectors on that particular instrument. So they cool them down even further, which gets rid of a lot of thermal noise. So that's what that's for. And also you can see one of the instruments itself in there. That is, here, I'll scoot around this way. There we go. That's FGS, which is a fine guidance sensor. That came from the Canadian Space Agency. We had ETU, which is an engineering model of the camera a couple years ago, and then they used the results of that test and made a flight camera. And we just recently electrically tested it before we put it in here, and it passed everything fine. And now it's integrated into here, and we will be connecting up to it actually Tuesday and running another series of tests to make sure that when it was transferred to this structure, it didn't get damaged.
So the structure's kind of black inside, or dark, dark gray. Why is that? We just see like silver or gold.
Well, it's for thermal reasons. The structure itself is made of, I'm not really 100% sure what composite it is, but it has a lot of good features in that when it changes temperature, the structure itself doesn't shrink or cool like as much as aluminum would, for example. That would be a lot more thermal contraction, which could throw off the optics. So this thing is extremely stable. The telescope, when it's in space and doing its job, in general, this portion of it at least is about -400 Fahrenheit. And obviously that's a big change from room temperature, so that's the reason it's made of this material, so that it doesn't contract and change sizes and things that can mess up the optics.
And I also heard it's very tricky working with that structure, even though it looks like it's very robust and stuff. It's hard to work around it.
Yeah, it really is. It's like I said, it's good in certain directions. It can't be. It doesn't have real good impact characteristics. So tapping in a tool dropping, for example, a wrench or anything like that would be a problem. So that's why there's all these. I don't know if you can tell, but there's pads all over, and that's when. So if you're working up above it or near it, really anywhere in it, in case anything falls, it'll hit a pad. That's the point of that.
For those of you who just joined us, we're talking with Mark Knappenberger. He's in the Goddard Space Flight Center clean room, which is the largest clean room in the world, and it's the location that we're building for the Webb Telescope, the majority of the Webb Telescope. If you have any questions you'd like to ask Mark, just check over here and fire away.
In the meantime, should I look around some more?
Yeah. One thing you talked earlier, actually Doug yesterday, how you practice in there, and there was a test unit of this structure. It's kind of interesting that you guys do.
Yeah, I'll walk around there. The harnessing on this was very complicated. There's a lot of stuff in the way, and we have to be really careful. Hoping I can get a little better look at the harnessing, but I don't think it's going to show up on the screen. But basically, there was again, an engineering model of that structure, and I'm walking over to it now. And that's right here. Hopefully that shows up. And you can kind of get a feel for all the spaghetti kind of cable that actually goes onto this structure. Okay, very good. Yeah, so this is where the harness lengths were kind of determined before the structure was built. The routing so that it wouldn't interfere with the installation of the cameras. There's a whole lot of things that have to be thought out well ahead of time before we actually get to the flight work.
So you guys you do a lot of practicing on test equipment like this before you get to the real stuff.
Yeah, and then even, like I said, even with the instruments and the electronics boxes, it's the same thing. We have engineering models that we run all our procedures on, electrical procedures, mechanical procedures, to make sure they're all sound before we go in and work on the flight stuff.
Hey, now, maybe you can tour us around a little bit more.
Sure.
The large structure that's in there.
Okay. Yeah, this item here is going to hold the primary mirror system. You can kind of see up at the top, there's like a small, again, engineering model to hold some of the mirrors themselves. That one in particular will hold 3 mirrors. But this whole giant structure is for the optics. And again, you kind of hopefully it shows up well on here. It's enormous. You know, the mirror itself is 6.5 meters across, you know, which is giant. Again, there's 18 segments that make that up. And that's all, of course, to collect as much, you know, light or infrared light as possible. Because this, okay, swing around.
Is there a mirror being tested?
Yeah, funny you should ask that. Let's see. Let me walk this around. Try to go reasonably quick here. This is a test mirror. It'll be coming up with a second there. Okay. All right. Let's see. Yeah, there it is. Down in the distance. I'll walk a little closer to it. Yeah, that's what all the mirrors put. All the 18 segments of the primary mirror look like this. I guess you can probably see yourself by now. There's that. And I'll go around to the back of it because the back's pretty interesting. Unlike a lot of telescopes, this one kind of has what's generally referred to as adaptive optics. And that means that they can actually bend this mirror so they can get into the kind of focus that they want. There's some of the electronics behind it. You can see some of the actuators, mechanisms. It's not just a flat mirror that's innovative. What is it doing? And that is in fact a gold coating on that mirror. And that's that reason because infrared light reflects off gold coating better than normal coating.
And for folks here too, the back here was actuators that I don't know if you've heard. Mark said, they can actually bend the mirror, and we have 18 mirror segments, so when they're all together, we have a system called wavefront sensing and control that will look at all the mirrors and analyze them and have them all adjusted slightly so that those actuators in the back can pull and bend the mirror so that all 18 mirror segments become perfectly flat or perfectly masked, so that it's as if it's just one mirror. So it is quite a system.
It is.
So Mark, if you can show, we got some hardware in there already, we got some other mirrors on this.
Yeah, let me, actually, since I'm an electrical guy, let me show you something electrical. One second.
Your assistant's, yeah.
We're experiencing technical difficulties. Okay. All right, I'm going to take you back to where the electronics are.
And you can get a question for you.
Sure.
Did you talk about the control systems on board? Structure itself, I'm just curious if you guys have what you have on there.
On the structure that holds the cameras?
You talked about capturing the mirrors itself, that you need to reorient the spacecraft. I was wondering what all you have on there. Do you have thrusters or gyros on there?
Yeah, I'm not sure if I'm going to be able to answer that right because I'm more electrical than that side of it. But there's no thrusters or anything like that. I'm almost certain that it operates the same way Hubble does as with gyros, just like you said. And the fine guidance sensor on camera I just showed you on there is the one that points at a star and controls the gyros to stay where it needs to collect the information that they collect. That helps. Sure, you're welcome.
So you were telling us about this unit.
Yeah, this unit behind you, I'm trying to get a good shot of the whole thing. It's basically the electronics compartment that control each of the cameras. So it's electronics. This first panel here, it's called a NIRI panel. That's an infrared telescope that came from ESA. And that's the electronics for it. And then the next bay over here, the first gold box is fine guidance sensor electronics. And the one behind it is all of the science data goes to that. It's called the ISO remote, ISO remote sensing unit. That's what it's for. Plenty of acronyms here. This panel we haven't populated yet. That's going to be for NIRCam, the one that's folded up. And this last one is near spec, and that's the electronics boxes for that camera. And that comes in. And this whole compartment runs at a reasonable temperature, close to 0 degrees Celsius. So it's not extremely cold, but by the time, this thing's about maybe 10 feet away from the actual structure. Over at the structure, it's much closer, like 270 below zero, and then firing out at the instrument is about 400 Fahrenheit, below minus 400 Fahrenheit. And all that's done through harnessing. Special wires that don't conduct heat well is one of the ways that they're keeping the heat away from the instruments themselves.
So you gotta keep the cool side cool and the hot side hot.
Yeah, exactly. I mean, like I said, all these things are, it is an infrared telescope, which means it's, collecting small heat signatures, basically, and we don't want to, you can't, that's why it's so far away, a million miles from the Earth. It's just to keep it out of, believe it or not, the heat that the Earth has, it puts off, and the moon even, just any of that will interfere with it. So it's always pointing out away from all that stuff. We'll never be using it here.
So, what are the hardwares in there? I got any light years and stuff?
Yeah, we'll go upstairs to Area 51.
I can get a question for you while you're walking.
Sure. optics allow you to change the focus if you need to by using the small actuators, as Mike was saying. So it gives you a lot of flexibility. Again, if Hubble would have had that, we could have tuned that mirror to get rid of the fuzzy problem that it initially had. So it's almost a belt and suspenders. I mean, you think you know how everything's going to turn out, but if you don't, at least you can adjust your mirror. So that's the reason for that.
Okay, great.
Sure. Now up here is some of the mirrors that have come in. They're all contained in these silver enclosures. Let's see. There's 7 of them. One of them's a flight spare. I was just looking at the schedule, and there's 3 more that are already delivered tomorrow as well. So they'll all be passed up here until they go out here under this, that big giant metal structure down there. And I think you can kind of get a little better feel of how big some of it is. Again, that wall is, each one of the major separations in the wall is about 10 feet. 8 to 10 feet. So we're up about 30 feet or so now, maybe. And you can see the big cranes that are going to help move the optics on top of that. There's also huge cranes above us that move stuff as well, any heavy hardware. Because in general, we don't like to pick up things here. We tend to prefer to let a crane do it. Takes a little bit of the natural man errors out of the shape.
Since it's always hitting from the sun, where does it get its power?
Well, the solar rays, the camera's just going to face towards the sun. The solar rays will still obviously get in the sun. So there's batteries, it's solar rays and batteries is where it gets the power.